The center of the Milky Way is an incredibly dense region, and there is so much gas and dust in the area that for the longest time, astronomers called it the Zone of Avoidance, that this region is opaque to visible light. But the term that I always like to use is it's not the Zone of Avoidance because there's something scary there, although there might be. It's the zone of don't bother, that if you're going to point your telescope at the center of the Milky Way, it's pointless because you won't be able to see anything. Well, everything has changed. Astronomers now use other wavelengths of light that allow you to see through that gas and dust and reveal the features at the center of the Milky Way. For example, seeing stars orbit around the supermassive black hole, see through the center of the Milky Way to map out the great attractor that's on the other side of the Milky Way. And now astronomers are mapping out enormous clouds of molecular gas surrounding the center of the Milky Way. This region is called the Central Molecular Zone, and we are learning so much about how stars can form really close to the supermassive black hole, how gas and dust flows in from outer regions of the galaxy, creating this bizarre, extreme, radiation-filled, star-forming environment at the center of the Milky Way. My guest today is Dr. Cara Battersby. She's an associate professor at the University of Connecticut and the lead of the Milky Way Laboratory. And Cara is part of a team that just released a 4-part detailed map in 3 dimensions of the center of the Milky Way, specifically the Central Molecular Zone. So if you want to learn more about the extreme environment at the center of the Milky Way, enjoy this interview with Dr. Cara Battersby. Cara, you are exploring a part of the universe that we were all told you shouldn't look, in the zone of avoidance at the center of the Milky Way. And yet, bravely, you continue on. What have you found there?
Yeah, I could never follow the rule. So yeah, this region I like to call the galactic Wild West because it's really where all of the laws that we're typically used to in our solar neighborhood just don't seem to apply. And we are trying to map out the 3D structure of our galaxy center, which maybe sounds boring, but that's not something you ever get to do in astronomy. You always just see one view. You don't get to see the top down.
And this region, I've been seeing a lot of stories about this, the Central Molecular Zone.
Yes.
How would you classify this area? What makes it different from places like the outskirts of the Milky Way that we live in?
Yeah, it's almost like a totally separate galaxy within our galaxy because it is physically separated from the rest of our galaxy. So our galaxy is a spiral galaxy. It's a flat disk, like a pancake. And at the very center, there's the Central Molecular Zone, supermassive black hole on the inside of that region. And then you have these dust lanes, these that go along the galactic bar that bring material from the outer edge of the galaxy into the inside of the galaxy. And that drives turbulence. It's partly what will drive accretion onto the black hole and have really exciting stuff there, possibly bursts of star formation. So a lot of really exciting stuff happening, but it's physically separated from the rest of the galaxy. It's not really touching besides these 2 bar lanes, which only bring material in. And also because it has this material constantly being driven inwards, these bursts of star formation, the supermassive black hole, the environment is very different than the rest of the galaxy. So it's like a weird little redheaded stepchild galaxy, within our own galaxy, just in the very center doing its own thing.
Now, this region is very extreme. People often talk about what is a habitable zone, a galactic habitable zone. And they think, well, you can't be too close to the center of the galaxy because it's a nightmare there, filled with radiation and stars on top of each other. Is it as bad as we had once thought? Yes. Or worse?
I would say it's definitely as bad as we once thought. Though, if you could have a civilization that could travel there, I think that could happen. I think having non-life evolve into life over billions of years is probably unlikely in the galactic center just because you are going to be close to supernova, you are going to be close to gamma ray bursts, you're going to be close to all of these exotic events. And probably even, one of the things we might talk about today is the fact that Sagittarius A star, or central supermassive black hole, has probably had active accretion periods in its past and possibly in its recent past, which would not be fun to be around when that's happening either, getting zapped with X-rays. But if you could visit, it would be beautiful. The night sky would just be lit up with stars. The stellar density is so much higher than what we're used to. It would be pretty incredible to see.
Yeah, I don't know what the average density is there, but it's kind of like being inside a globular star cluster,
Yeah,
like
that's right.
just a
Yep.
light year apart to see your
Hmm.
next
Yeah.
star. But the big surprise that I think has been unfolding over the last couple of years is how much star formation is going on right near this central supermassive black hole. Why did we think that there wasn't star formation?
Yeah, that's a great question. So I think that the my basic understanding of it is that, you know, the gas is that we don't really see a lot of gas there. And so where would the stars be coming from? How would you have a population of young stars if you don't have the gas from which they formed? And part of that is that it's hard to tell where the gas is physically located. Like you see it in projection at different places in the galactic center, but like, is it physically close to the black hole, or is it way in front of it, or is it way behind it? And so just understanding basic things like that, like if you don't even have like a good geometrical picture of like what it looks like how can you say whether or not stars could form there? And it's also just like a very extreme environment. So any gas that would be there would be like highly turbulent, really hot, and probably moving really fast. And so then how do you do this thing of like slowly collapsing to form stars into the slow, like gravity is like not the strongest force, right? And it takes time for it to happen. So how would that happen in this chaotic environment? But the universe finds a way.
And I mean, I've been reporting on star forming regions that are shockingly close to the
Mhm.
supermassive black hole, like really right next door, probably interacting in the outskirts of it. It's crazy. And yet there they are.
It's crazy. It's totally crazy. And I mean, this is why we go where we're not supposed to go, because
Yeah.
this is where some of the most extreme physics is happening. And, compared to these distant galaxies that James Webb is seeing, this is basically right under our nose. Like you can see the individual stars next to the black hole. You can't see that in a galaxy halfway across the universe.
And there have been a range of instruments that have participated in this new survey of the central molecular zone. The ones that I'm most fascinated with are the images coming from the radio telescopes, like
Mhm.
Meerkat, seeing these enormous filaments. A lot of these, again, were giant surprises.
Yes.
What do we think is going on?
It's a little bit like, I feel like our perspective of it is a little bit like how people used to think of the sun. I mean, I think a lot of people think of the sun as being this perfect celestial orb in the sky. But when you look at it closely, like you see these giant solar prominences and solar flares coming off of it, these twisted magnetic fields. I think it's very similar to the galactic center in that way, where, we don't have that many great ways of measuring magnetic fields. And, it's a very common joke in astronomy that at any talk you could go to, you could just sit in the back, not pay any attention, then just raise your hands and say, well, what about magnetic fields? And,
I've heard that. Yeah.
yeah, and that they would just say, oh, shoot, like we didn't consider that, or we don't really know how it would affect it because we know so little about it. But when you look with like this Meerkat data, I think that you're talking about in the radio particularly, you see these crazy long skinny filaments. And the best way to explain that theoretically is almost certainly with like these magnetic fields, and you have these charged particles being trapped around those in the synchrotron radiation. So that's almost certainly what we're seeing, but we're like little tiny babies in our understanding of the magnetic field in this region.
And I mean, I'm trying to remember if I'm remembering this correctly, but there's like really strange, almost outflows and inflows that are connected with these. They look like space tornadoes, and then you've got that in this larger environment where these flows are coming in from along the bars, as you mentioned.
Mm-hmm.
It seems like a much more dynamic region than anybody had predicted.
Yeah, I think it's so dynamic that like what we use this term called dynamical time in astronomy, which really just means like how long it takes something to orbit around, like just roughly on what time scale are things changing dynamically. And in the galactic center, it's like the same time scale as which stars are forming, for example. And so all of these principles that we developed about here's how a star forms, cloud slowly collapses and da 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 da, are going to be different when that cloud is also being sheared apart at the same time scale as what's happening there. Yeah, so I'm obsessed with it. I think it's super fun. I love it. And I'm glad you're excited about it too.
What role do you think the supermassive black hole is playing on this environment?
Yeah, so right now our black hole is quiet. It is not saying very much at all. It's not accreting material, but when a black hole does accrete material, it usually spits some of it out through the poles and can have these really disruptive events that will, like we talked about before, would be very harmful for life in the vicinity, but can also really just shape the entire structure of not just the central molecular zone, but literally entire galaxies can be shaped by this active galactic nuclei, AGN activity. And so, but one of the things that like I'm super interested in is we don't really know when the black hole feeds or why it sometimes is active and why it's sometimes not active, because you need to understand where that gas is, how that gas is, when it's accreting and what's controlling when it's accreting. Because when it does, it can have these little burps, these little flares, or it can have these huge things that will just blow giant holes in the galaxy and change the evolution of the entire galaxy.
And it is interesting. There was a paper I reported on just a couple of weeks ago talking about people were watching sort of various quasars turn off and on in real time. I mean, obviously delayed by the speed of light, but it really looks like this process is very quick, that you've got, it's a quiet black hole and then suddenly, I don't know, a meal comes by and it wakes up and snaps at it. And then you're seeing this burst of radiation. And then this has got to be changing the environment in this central molecular zone. And then it goes to sleep again. I guess then stars get to form, or I don't know.
Yeah, no, that's exactly right. And I mean, this is different than how we've done astronomy before, where the heavens are unchanging. I draw a picture today and, it'll be the same again tomorrow and the next day. I mean, because these things are happening quickly. So you need to have telescopes that are being responsive to this. You need to change the way that you're thinking about it, the way that you're looking at space. And again, I mean, I think that doing this over the entire universe is really important because you need to understand like all the different phenomenology that's happening. But I'm really excited about our own galactic center in particular because we do get this sort of front row seat and we can understand that star that was right next to it. Like maybe it's going to eat that someday.
Right.
Yeah.
And so you mentioned earlier that this is being done in 3D. That we're actually, so explain exactly how you do this. How do you get this sense of these are the things that are closer, those are farther, and what's happening sort of in this larger three-dimensional picture?
Yeah. Okay. So as I said, our galaxy is like a spiral disk in the like a pancake, and so we are unfortunately like deep embedded within the pancake of that galaxy. And so anytime we try to look towards the center, we're just looking through all of that stuff in between. And you're really only seeing this side view perspective. So anytime you've ever seen a picture of the Milky Way, it's always a artist rendition. And that's because, if you could send a spacecraft up above the Milky Way and look down and take a picture and send it back, it's like many thousands of light years away. So even if you traveled at the speed of light, you're talking about several thousand years before you'd get anything in return. And so we're just trapped with like this two-dimensional view of our galaxy. And so you have two dimensions. So you have position and position along the plane of the sky. And we also get velocity. And so that velocity tells us about how the gas is moving. This is using the Doppler shift of the gas. Which is super cool. So that is like 3 dimensions, but it's not necessarily the 3 dimensions that you want. You want to know where it is along the line of sight. So one of the tricks that we used is something that we realized is that so many models of how the galactic center is, how the gas is flowing, where the star formation is happening, when the black hole is going to feed. It depends on this 3D structure. But because you're just looking at it edge on, you don't get to see that 3D structure. But the galactic center is really bright at all kinds of different wavelengths. And so if you have a cloud that is in front of the galactic center, this is one of these cold, dense molecular clouds. It is actually going to absorb that light from the galactic center. If it's behind it, you will not see the absorption towards that cloud at all. And we see very prominent absorption towards several of these galactic center clouds. And, I think people have intuitively known for a while, like, oh, that one's probably in the front of the galaxy because I see this extinction. So that means it's in front, like literally like if I put my hand in front of my face, my hand's in front of my face, like my hand's behind my head. It's the same thing, but with molecular clouds and a very bright galactic center. And so we're really the first ones to do this in a quantitative way. And so we've combined a bunch of different techniques using really simple dust extinction, but also spectral line absorption. and done a probabilistic combination of all of these to uncover basically the likelihoods for every single cloud. What is the likelihood it's in front of us, in front of the black hole, and what is the likelihood it's behind the galactic center?
And how far can you go with that? I mean, in optical light, the center of the galaxy is opaque.
Yeah.
But once you go into other wavelengths, infrared, radio, and so on, then you're starting to be able to see that. Are there still limits, or can you see right through the galaxy in these other wavelengths?
Yeah, great question. You can see right through the galaxy in these wavelengths. So once you get to about 100 microns, as you go to like the far infrared, everything is pretty much opaque, totally optically thin. You can totally see the entire galactic center in those wavelengths. And then if you use a combination of the shorter wavelengths, you can see how the extinction changes and use that to understand more about the relative distances. I'd say there's a lot more that can be explored. And so in addition to the papers that have been published online, my graduate student, Danny Littman, she's been leading a lot of this work, and she is doing a synthesis paper now, like incorporating even more data into this. And I think that there's really no limit to how much more data we can add to this. The limitation will always be that we don't a priori know what the background is behind what we can't see. And so you'll always be limited by that. But so for one single cloud, I probably wouldn't bet my life savings on, it's exactly at this position. But if you get a statistical ensemble of a bunch of them, I think that I'd bet my life savings on that being approximately correct. Yeah.
Right. And again, I'm sort of imagining these clouds in this very dense environment. You would think that the galaxy would have used up these sources of this cold molecular gas to form stars a long, long time ago.
Yeah.
And yet there it is, and potentially stars are still forming. Why hasn't it gotten around to this, already?
Yeah, I would actually say it has. So it has. That's why we have this like enormously high density of stars, because so many of these previous generations of molecular clouds have gone on to form stars. And then the gas that's expelled from those, like some of that might be actually controlling what goes on to form the black hole. It's because the galaxy just keeps dumping more material in. So you have this constant inflow of material. Almost 1 solar mass per year is coming along these dust lanes and landing in the central molecular zone. Whereas like right now, the star formation rate is only about 0.1 solar masses per year. So right now that gas is just building up, and we're probably going to see a big burst of star formation, would be my prediction, in, 5 to 10 year. That would be cute, wouldn't it? 5 to 10 million year time scale.
Yeah, let me just check my watch. Yeah. Check back in 5 years for all those new stars. Yeah. But because it's such a, so much radiation going on in this area, and like I know it needs to be cold gas for you to be able to get those stars forming, and yet you've got all of this intense radiation and the interactions with the black hole. Like, how is this gas not just getting too heated and glowing in X-rays or whatever, and not actually, able to turn into stars?
Yeah, I mean, a lot of the gas. So the gas in the galactic center is generally like way hotter than the rest of the galaxy, which is why I said it's sort of like a little galaxy within our own galaxy that just has totally different properties. So one of them, like as you rightly described, is the temperature. So the temperature is way higher in these regions. So it is harder for stars to form. So one of the things that's been coming out of studies in the last decade or so is that if you look at the amount of dense gas in the center of the galaxy, which is where we know that stars have to form, there's way more of it than the star formation rate would say. I guess the other way, saying it the other way would make a lot more sense. So the star formation rate is relatively low for how much dense gas there is. And that is precisely for what you said, because the gas is so hot, and it also the turbulence, just the general, like it's moving around, it's shearing out, it's spinning. It just makes it hard for gravity to take over and to collapse it. But because you have this constant inflow of gas, one hypothesis that I'm a big fan of is that it's like too hot and too turbulent to add to like form stars, but it's in these stable orbits. So it just orbits, and then more gas just keeps flowing in. And eventually you get so much gas that like, even though it's hard for gravity is just like, well, just going to collapse it anyways. There's just too much gas here.
Might as well.
Yeah.
But I mean, with star formation, often you need some kind of event like a supermassive black hole or the gravity wave of a spiral arm sweeping through a region to begin this process. Are there those kinds of events going on in the center of the Milky Way?
Yeah, we think so, but this is one of the reasons I'm so excited about the 3D stuff, because, you just see this like side view of the galactic center. And so we think there might be certain spots that are where the star formation is being triggered, but that's really hard to trace if you don't know what's in front and what's behind. So, but my former student, H. Perry Hatchfield, he wrote a paper about simulations of gas flowing into the center of the galaxy. And star formation sort of found that there is these star formation hotspots that basically, like, once the gas is flowing in, it sort of crashes into other gas. And some of that will just spin out and go away, but some of it will that'll trigger the collapse of some of the stars. And so that's actually, we think, maybe triggering some of the star formation, but we can't actually test that until we know what the 3D structure is.
Are there supernova remnants in the area?
Are there ever? They're everywhere. They're all over. I mean, and that's one of the other things you'll see in with these radio maps, all those big bubbles. A lot of those are just these massive supernova remnants just dominating the landscape. They'd be all over the place. Yeah. So, like, the metallicity is like higher in the galactic center as well, which is something we haven't.
That was going to be my next question. Okay.
Yeah. Significantly higher. Yeah.
And that's just because so many more supernovae are going off in this area.
Exactly.
Wow.
Yep. Just more generations of star formation have happened. Yeah.
And so, you are sort of working on a similar version, but with other instruments. So, talk about your work now with ALMA.
Yeah. So we have a new large program with ALMA. So ALMA is this interferometric radio telescope, submillimeter telescope in the mountains in Chile, like 64 giant antennas. And I won't talk too much about interferometry except to say that it's like black magic. You take the...
It's okay. My audience is very familiar with interferometry. You don't
you take the signal from all these different antennas and you use black magic to get much higher resolution. So we're doing this that's what ALMA is doing. And we have a large program towards the Galactic Center called ACES, ALMA CMZ Exploration Survey. Gotta love an acronym within an acronym. And we're mapping out the entire Galactic Center for the first time at this really high resolution. And so in a bunch of spectral lines as well. So, like, not only getting position, so like what the map looks like on the line along the plane of the sky, but the velocities as well. And the velocities in different tracers. So, like, where are the shocks happening? Where are the stars forming? And that really helps to build up these 3D models.
And so what are the big unsolved questions right now about the center of the galaxy? Yeah,
there's almost too many to count, but I will just highlight a couple of big ones. So one of them is, we want to understand how stars form across the entire universe, because stars are life, not just in like the really direct way of our star is responsible for life on our Earth in terms of providing all of the energy that we as humans and plants need. But it's also, you track a galaxy by the stars, how enriched the material gets is from stars. Our bodies are made from the insides of stars. It's all driven by stars. But we have like a very limited sample size of how stars are actually born. So in our own solar neighborhood, you have like these very kind of tame properties of turbulence, gas temperatures, pressures, Stars form in this clean, simple way. But most of the rest of the universe is not like that. And our own galactic center gives us a chance to see, like, when you have all this crazy physics and you throw it together, how does that affect the star formation process? And what we're finding so far is it's not following the same laws that were developed in our solar neighborhood. So that could have impacts for the rest of the universe. The other big thing, if you'll let me, is just that I really want to know, like, how this whole ecology works. Like, when does a black hole feed? What decides when that material gets onto the black hole? And what decides when you have these big bursts of star formation? And because that's like affecting how galaxies evolve over cosmic time, like, I'm so fascinated by that question. And I just love that in our own galactic center, we kind of get this firsthand view of that. And like by combining a lot of data sets and especially simulations, you can sort of zoom backwards in the past, zoom forwards, and sort of just see like it's like the lifeblood of galaxies. Like how are they changing? How are they evolving? Yeah.
And how do our observations of the Milky Way compare to other galaxies that are within reach? I mean, we're able to look pretty well at the large, small Magellanic Clouds. We can look at Andromeda. Things get a little murky. You know, maybe we can look at the vicinity around the supermassive black hole in M87. Do we have a sense if, you know, are we normal?
Yeah, the Milky Way seems to be very boring. So sorry if that was not the right answer.
Well,
but
I don't know. Is boring normal?
yeah, it's very normal. It's very, very normal. And I mean, I guess the good pros and cons. So one of the pros of that is like we're a good place for life to form. So maybe other galaxies are a good place for life to form as well. And I guess one of the cons is that there's some extreme physics that we don't get to see up close and personal. But yeah, the Milky Way is pretty normal. Yep.
And in the future, when we do collide with Andromeda, how do you think that will change the environment?
Yeah, so that will really depend like where the collision happens. So there's a lot of possibilities. I'm sure you and your viewers know that, you know, the likelihood of actual stellar collisions in when galaxies collide is super low. So that's not likely to happen. But one of the things that will change is like these nice orderly dust lanes along the bar that drive material into the CMZ will get completely disrupted because gas will definitely collide with gas and it will change the orbits. It will form new stars where those things are intersecting. The black holes may merge. And like you'll just have twice as many stars in the sky at night. So there'll be that to look forward to. But also that may cause the black hole to like merge or like to feed on all that new material and have like a big outburst that then reshapes our galaxy in other ways, which maybe wouldn't be so good.
But I wonder what like a binary black hole would do to a place like that. You know, when our supermassive black hole and Andromeda supermassive black hole are finding one another in this new, you know, giant merged galaxy, that sounds like a mess.
It does. And there's, you know, this is getting beyond my area of expertise, but I do know some basic things, which are that, you know, we don't really know exactly how the black holes merge or on what timescales that's determined by. There are some like physics problems that, you know, we don't know how to overcome in terms of like how they merge, but we know that they do merge and people are studying this using multi-messenger astrophysics with gravitational waves, but it's a big area of open questions and mystery.
Cara, what are you obsessed with?
So many things. I'd say like my latest work obsession is answering this question of the 3D structure. So like our papers, we were getting really close to it, but we have more, and then we're actually combining with the simulations now. And there's so many questions in astronomy that people have been asking for decades and decades, and like you make incremental progress. But I think we can answer the question of what the 3D structure is. And then that just opens up this whole big can of worms, not can of worms, like good can of worms. What is that called?
More questions.
I don't know. Yeah, more questions of like all these awesome questions that we can answer. The other thing is I'm working on a big project with NASA. It's PRIMA, the Probe Infrared Mission for Astrophysics. We just got selected for Phase A with NASA, which means they gave us $5 million to like write a more detailed proposal about how we'd build this probe concept to do far infrared science and open up some questions about our own galactic center, looking at other galaxies across cosmic time, protoplanetary disks. And that's just like really exciting to think about, like a new spacecraft that could be built. And we're talking about 2030s timescale, but I have to be obsessed with it because it's a lot of work for something that's not real yet. So
yeah. I mean, the far infrared is a real gap in our ability to see right now, especially since Herschel and Spitzer are no longer, like, are there any far infrared space telescopes operating right now?
Yeah. And Sophia was like this really cool jet that they refitted to have a small far infrared telescope that would fly just high enough in the atmosphere that you could get above most of it and see. But otherwise the atmosphere blocks all of the far infrared. And there's like nothing right now. So there's this huge window of like opportunity that I really feel like we need to take advantage of.
And it is a more forgiving wavelength because it is so long that it would work very well as an interferometer. So are you guys, are you going to pitch a far infrared interferometer?
I wish. Yeah, everything has to be, I don't know if you do know, a TRL, technology readiness level. NASA does its job well. I mean, but they're not risk takers. So, if you want to do far infrared interferometer, you got to go with a smaller scale mission, do it like on a smaller scale. And so they really want something that's proven, that's ready, that they are very confident is going to be successful, which unfortunately is not, an interferometer at this point. But I think that'd be really exciting in the future. I'd like to see that happen.
Yeah. So this would be like a successor to Spitzer.
Yeah.
Yeah. And then, I mean, just give me a comparison. When you sort of think about the kinds of discoveries that Spitzer was making, or Herschel, would there be any new wavelengths that you would be hoping to see, or would sort of fit within those existing wavelengths? And then what kind of resolution compared to what's come before?
Yeah. So resolution is actually not going to blow your socks off. It's actually comparable to what we had before. Again, because we're just looking at like a kind of a small telescope that fits in the back of a spacecraft and just can be launched as is, not opened up like James Webb. But sensitivity is what's going to blow us out of the water because we have like these new detectors people have been working on for like the last decade or two. And you are basically improving like your sensitivity and mapping speed by like a factor of 100,000. And so, with Herschel, we did like a couple of protoplanetary disks. With PRIMA, we would do like, all the protoplanetary disks. And we wouldn't just do a couple of galaxies. We'd do like thousands and thousands of galaxies and get really good statistics.
Like, I think about, say, the images that we get of protoplanetary disks from ALMA, these really cool little spirals and concentric rings and things like that. So would we get something that is comparable to that, but in the far infrared, higher resolution? Would it blow those out of the water?
So the pictures are not gonna, again, because of like spatial resolution. So if you care about pictures, it's not the telescope for you, but the spectra is actually what has so much of the science in it. So that's where you find out like, where is the water in a protoplanetary disk? How do exoplanets get their atmospheres? Like where do their oceans come from? Those are the kind of questions that you can answer with the spectroscopy. And so, you don't get these like really beautiful pictures, which I'm a visual person. Like I love the pictures as much as anyone, but spectra have so much information. You're talking about velocities, the structure of that, temperatures, and all these different species that you can trace out. So there's really just this huge gap between what ALMA can cover and what James Webb can cover. And like there's, most of the light that has ever been emitted in the universe is in that wavelength range. It really is. Like, so more than 50% of all the lights from stars comes out in the far infrared because it gets reprocessed by dust. And that's all just completely hidden to us. So not only just...
Really?
Yeah.
Huh. I had no idea.
Yeah, it's huge. And it's not just, so there's like that visual part of it, right? That just like a bunch of the light that we're just missing, but there's so many interesting and important spectral features, like in particular with disks, we're looking at ices, and you don't get to see those ices at other wavelengths. And HD, which is a really good tracer of like the total mass of a disk of a galaxy. In like galaxy science, you get the tracers of star formation and active galactic nuclei at the same time in like thousands of galaxies. So you can see like, how are these things related over cosmic time?
I mean, we've been getting all of these news releases from James Webb on exoplanets, and it's just a spectra, and people seem to be okay with that. So, people are like, where's the really cool pictures of exoplanets? And all you get is just a bunch of squiggly lines that show you where the oxygen is and where the methane.
None of the pictures of exoplanets are real though, right? They're all just the artist rendition. So
yeah. Because all you get is one pixel. But if you're into spectra, which you should be, then seeing those wiggly charts that show where, all the proof of the different chemicals in the atmosphere, that's the exciting part.
That is exciting. Yeah. And if you want, we can make artist renditions of those protoplanetary disks based on the spectra. So
right. So, but more importantly, you'll have the spectra, and that will give people a good sense.
That's where the numbers are. That's where the science is at. Yeah. So
if all goes well, when are you sort of hoping and targeting for a launch?
Like 2030, 2032 or so. Yep. So
That's
not
not that far
forever.
off.
That's like, yeah, exactly. That's
Yeah.
within my career. That's you'll be reporting on it. So
Yep. Yeah, absolutely.
yeah.
Awesome. Well, good luck with
Thank you
that.
so
And thanks for
much.
taking the time to
Yeah.
chat with me today. I really appreciate it.
Yeah. My pleasure.
I hope you enjoyed this conversation with Dr. Battersby. Now, we had a separate conversation about astronomical simulations, about how astronomers can take these very complex fluid environments and simulate them in a computer so that they can understand this better, and the kinds of training runs that they do, how big these computers are and what's involved, and how you can get a sneak peek of the data as it's coming out. So we've got this longer version of the interview over on Patreon. We call that Interview Plus, and I'll put a link in the show notes. It's completely free. There's no ads. You can watch it right now. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Braley Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bayluck, Cy Nelson, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Mattern, Jim Berg, Jordan Young, Marcel Smits, Michael Purcell, Modso, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Thomas Ilskadron, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. I've got to admit, I've been really obsessed with the center of the Milky Way, and there's been a bunch of things that have been coming together. One is the new capabilities of James Webb. We've been seeing a lot of really interesting observations in this area, and I had just had no idea that there was all of this star formation going on. And then in the last couple of years, I've been doing more and more reporting about this. But the other thing is these images from Meerkat in radio waves of these bizarre tornadoes that are visible at the center of the Milky Way, these giant filaments that are hundreds of light years across, and their interaction with the other gas and dust in this area. And so it was great for me to be able to finally find somebody who is specializing in this to answer all of my questions. Now, I've done lots of relevant interviews sort of in this same area, so we'll link to some of those in the, it'll be around here somewhere and in the show notes. All right. Thanks a lot for watching, and we'll see you next time.